Chemistry students, welcome to your lesson on calculating with hydrates. So, in calculating hydrated ionic compounds, you may remember that when we were studying nomenclature and we were studying ionic compounds, we talked about a certain kind of compound called the hydrate. Hydrates are formed in an aqueous environment, and because of that, the ionic compound, it traps some water within its matrix, and so part of the mass of the compound is just water trapped inside. So for example, here we have magnesium chloride hexahydrate. Here's the magnesium chloride in the middle. All around the outside, there's kind of like a cage of water molecules surrounding the magnesium chloride. And so in the matrix, the matrix of magnesium chloride material, we've got water there as well. So this is the hydrate, and the chemical formula for magnesium chloride hexahydrate, not surprisingly, so it's magnesium Mg Cl2, so 2 chlorines for every magnesium, and then for every molecule, for every compound unit of magnesium chloride, you've also got 6 waters on top of that. So if you're to apply heat to the magnesium chloride hexahydrate, okay, so you had some heat, you would end up evaporating the water away. It would pop out of the solid, and you would end up with just MgCl2 left over, okay? And this is called the anhydrate. Anhydrate. So here we have the hydrate, heat it up, and you end up with the anhydrate. Another example is copper sulfate pentahydrate, okay? So that would be copper sulfate, CuSO4, multiplied by penta means 5 H2O, okay, and that's the nomenclature, and here you can see the picture of it. So we've got 1, 2, 3, 4, 5 molecules of water surrounding copper sulfate in the middle. And if we apply heat to that, we can also evaporate the water away. So take away with heat, and we end up with just the copper sulfate. Okay, so this is the anhydrate, and over here we have the hydrate. And that's the basic idea here. Hydrates are made up of part water, part ionic compound. So water, as we've been saying, water is included here in the chemical equation for the hydrate. It's also included in the molar mass for the hydrate. So for example, here with magnesium chloride hexahydrate, the mass, the molar mass of it will be equal to the mass of magnesium chloride. So magnesium is 24.31. Chloride is the 2 times 35.45 plus, and then 6 times the mass of the water. So 2 times 1.01 plus 16. Okay, all in all, the anhydrate weighs 95.21. Oh, and I should have put as units grams per mole. Grams per mole. The anhydrate is 95.21 grams per mole, plus the water component of it is 108.12 grams per mole. Okay, all in all, add them together, we get 203.33 grams per mole. Okay, similar calculation for copper sulfate. Just going to switch to black here. The mass is going to be mass of the copper sulfate plus the mass of 5 times the mass of water. So 63.55 is the mass for copper, plus 32.07 is the mass for sulfur, plus 4 times 16 is the mass for oxygen, plus 5 times water, 2 times 1.01 plus 16 grams per mole. Okay, the anhydrate works out to 159. And the water component works out to 90.1. All in all, the mass of copper sulfate pentahydrate is 249.72 grams per mole. Okay, pretty simple calculation there. Moving forward though, if we're to analyze that copper sulfate pentahydrate and ask ourselves what is the percent composition of the water in the hydrate, in the copper sulfate pentahydrate, what we could do is just very easily calculate that. So the percent by mass of water would be equal to, and we look up here, the water in this case was 90.1 grams per mole. Divide that by the total mass of the hydrate, which is 249, and multiply that by 100%. That gives us our percent composition of water. Okay, and that works out to be so 0.3608 times our 100%. Okay, so that's the first type of question you might be asked about hydrates. The other type of question you may possibly be asked when it comes to hydrates is calculate for a certain compound how many waters are there in this hydrate. So here's an example question like that. For a 50-gram sample of barium hydroxide hydrate, we've got 27.2 grams of barium hydroxide. So find the value of X in the general formula barium hydroxide something hydrate. Okay, so starting out, perhaps perhaps what we want to start to do is just write out what we know in terms of the masses of the different components. So the molar mass of barium hydroxide is going to be equal to the mass of barium, 137.33, plus 2 times the mass of oxygen plus the mass of hydrogen. Okay, and add all that together, multiplying it out, you end up with 171.35 grams per mole. There we go. And then the other component of this compound obviously is water, and the molar mass of H2O is just 2 times 1.01 plus the mass of oxygen, 16.00 grams per mole. Okay, is equal to 18.02 grams per mole. Okay, so those are the two masses. Yeah, so if we had to calculate the percent composition of barium hydroxide in this barium hydroxide hydrate, what it would work out to be would be, okay, so percent composition barium hydroxide. Okay, so it would be the 171.35 grams per mole divided by the mass of the entire barium hydroxide something hydrate, which would be 171.35 grams per mole, plus some value X times the mass of water, which is 18.02. Okay. We can't really simplify that anymore, but we do have some information that we could relate this formula to. So if we look up in the question, we notice that we're given a 50-gram sample which contains 27.2 grams of pure barium hydroxide. That's the anhydrate. So we can just equate those two things. So percent composition from the sample is equal to 27.2 grams divided by 50 grams times 100%. Okay, and that works out to be 54.4%. So just about half of the mass of the barium hydroxide hydrate is tied up with barium hydroxide. The rest is water. So now we can equate those two things. So again, taking our formula from up here, we have 171. No, that's okay. So 171.35 over 171.35 plus x times 18.02 is equal to, okay, and this will be times 100% is equal to 54.4%. Okay, we're simplifying this a little bit. 171.35 over 171.35 plus 18.02x. Okay, take away the 100% is equal to 0.544. Next step, I'm going to multiply both sides of the equation by 171.35 plus 18.02x. So on the left, I'll have 171.35 left over. Okay, 171.35 times 0.544 is equal to 93.21 plus 18.02x times 0.544 is 9.802x. Okay, and then I just solve for x here, so I'm going to end up with 9.802x is equal to 171.35 minus 93.21. A few steps down the road, solving for x, you should end up with 7.97 was what it works out to, or it's approximately equal to 8. We're going to round up. So, in other words, for every compound unit of barium hydroxide, I'm going to have 8 units of water. So this compound that we've been dealing with is called barium hydroxide octahydrate.